Chapter 7 now. We're in the second part of our trig. We're looking at trig equations and identities. That's what this chapter is about. It's now taking what we've learned from your functions chapter, and in essence we're finding the zeros of graphs usually, or intersections of graphs. So let's look at what we've got in this one. The first one, Ferris wheel question. We've seen these many times already. Whoops. There we go. Let's use a highlighter. Taking this graph, plugging it into our graphing calculator, we get our curve with that window setting. Then the question that we're being asked is, to the nearest second, when is the first person a height of 10 meters? So we plug in our 10 for our second graph, and we look for our intersection points. The first one is going to happen here. Plugging her in, we got our intersection point, and we want to make sure that we are closer to the first intersection, and then that's first curve, that's the second curve. Yeah, let's find the intersection between those two. And we get, there we go, 7.36, or sorry, 38. So 7.38. Now the big question though is, how could we do it algebraically? Okay, that's going to be more in 7.2, is dealing with the algebraic method. But in order to find it, we would just plug in our h of 10, and work her through. Negative 15 cos 2 pi over 40 t plus 16. And now we would start isolating and solving for t. Okay. So we'll write that there. Isolate. Solve for t. In this type of a question, we've got y1 and y2. Or equate it to 0, which I often will do so that I don't have to look for it, and find the zeros. So either in this one we're finding our intersection, oops, spell it right, finding the intersection, or in this case we would be finding the zeros of the graph. So I'm going to do the first one by finding the intersection method. Graphing the first side, graphing the second side, we need to change our window. We know that our domain is from negative 4 pi to 4 pi. So let's change that. So we've got negative 4 pi to 4 pi. And scale, hey, let's do pi over 6 for the fun of it. Doesn't really matter what you do with the scale. And then our y values. We've got to decide where we're going to go. Hey, this is a sine graph that we're doing, so I'm going to say, let's do, I don't know, negative 2 to 2. Scale 1. Graph that. There's our first one, our sine graph. And right there's our negative 2/3. Find the intersection point of each one of those. 1, 2, 3, 4, 5, 6, 7, 8 spots that we're going to have to find. I'm only going to show you doing the first one, and then I'll give you the answers. You can work through the rest of them yourself to make sure you can do this. So we're going to go second, calculate. We need to find our intersection points, and I need to take it way over to the closest, or oops, way weird, what happened there? There we go, back on line. Okay, I got to go closest to this intersection, the first intersection. Now, if I'm on the sine of x graph, it's going to take me a while to get there by scrolling. If I jump down to the line graph, the negative 2/3, I can get over there a little bit faster because I don't have to go up and down. So just be closest to that one. Enter, enter, and we get, boom, there it is, negative 8.695. So we're going to say to the nearest hundredth, negative 8.70 is our first one. We would do the exact same thing going closer to the next intersection point. The next one gives us negative 7.01, then negative 2.41, then negative 0.73, then 3.87, and 5.55, and then 10.15. Whoops, that looking like garbage. And then 11.84. There's all of our intersection points. Those are the x values that solve and satisfy this individual equation. Now let's jump to our tan. I'm going to do this one by doing the zero method, just to show you the opposite method. So then that gives us tan of x minus 2 equals 0. We're going to graph y1 equals tan of x minus 2 and look for the zeros of the graph. Let's do it. Okay, so I've got my one equation in, only have to worry about one of them. But we got to change our window slightly because we only let our max and min be at 2. I guess we could keep it as that. We're looking for zeros. It's all good. We're going from 4 to 4. Pi's. Nice. Let's graph that and find our intersection points, or our zeros, I should say. Okay, the vertical lines, those are the asymptotes. They're not part of the graph. Let's go second calculate, and we're looking for our zeros of the graph. And let's go over. Where are we at? Gotta go scrolling over, get close to the last. There we go. That's odd. Okay, I need to have one below and one above the axes. Enter. Make sure that your arrow up at the top is pointing in towards your zero. And enter. And that one, well, gotta check what I did there. All right. I think I hit the over button one too many times there. And I was into the next part of the graph. So when we get our 0, one on the left, one on the right, we get, there we go, negative 11.45. So our first one is negative 11.46, and then I'll just give you the next ones. Negative 8.32, negative 5.18, negative 2.03, 1.11, 4.25, 7.39, and 10.53 would be all your intersection points. So I've just given you the two methods again of finding your solutions graphically. First method, graph equation 1, which is one side of it, graph equation 2, which is the second side, and we look for our intersection points. There and there. Method number 2, equate it to 0, graph just 1, and look for your zeros, there and there. You'll get the same answers both ways. Because this is a periodic function, and this function goes on and on in both directions, right and left, if we increase to 4 pi's instead of 2 pi's, we're going to have more and more solutions. And all those solutions are going to be related to each other. So this is on the way down, on the way down, on the way down, on the way down. All of those solutions are related to each other. All the solutions that are going on the way up of the graph are going to be related to each other. So we have two sets of the solutions, and those come right back from the first solutions that we got. The red one was 0.37, the first positive, and the blue, the first positive blue one, was 3.85. What that leads into is called the general solution. When are all the red solutions going to happen? When are all the blue solutions going to happen? It all has to do with what's the period of the trig functions. Cos has a period of 2 pi. Sine has a period of 2 pi. The period on this whole equation is going to be a period of 2 pi. Which means between every red solution is going to be 2 pi. Between every blue solution is going to be 2 pi. So our general solution is going to be that x equals the first positive, 0.37, so first positive solution, plus any multiple of the period. So whatever the period is, slap your n in there, any multiple of the period. Now you got to define your n, n-e-i. This book will always show it as a k and a z. I'm going to use n-e-i because that's what they use on the diploma. Cookie cutter. Now we take our second positive answer and we do the same thing. Add the period, slap the n on, NEI. Done. Looks like this. X equals 0.37 plus 2n pi, 2 pi, and I slap the n. Where you put the n doesn't matter. Put it on the end, put it at the beginning. I don't care. I'm going to always put it in the middle because that's how you're going to see it. And then define your n, N-E-I. Second positive, which is your blue, plus your 2 pi, slap the n in there, N-E-I. Done. That is your general solution. Okay, so to do this one, either graph left side, right side, find the intersection, or equate to 0, find the zeros. It is safer to equate to 0 and look for your zeros. So y equals, let's go, bring everything over to one side. I'll say 2 cos squared x minus 5 cos x minus 1. Let's graph that. So we got 2. In order to put cos squared is saying the same thing as cos of x in brackets squared. So that we don't always have to write the brackets, we put the squared inside the part of the trig function. So punch it in, bracket, cos x bracket squared minus 5 cos x and the bracket minus 1. And let's graph it. And I'm going from 0 to 2 pi, so I need to change my window from 0 on x to 2 pi. Good. Graph it. And we're looking for any x-intercepts that are going to emerge. Oh, there's 2 of them. We go, find our zeros, same way we've always found the zeros. When you're trying to find where your cursor is, make sure you watch this bottom bar here. It tells you where your x and your y is. Right now I'm above the x-axis because that's a positive value. There it comes. Perfect. 1 to the left, 1 to the right, and find it. So 1.76. So x equals 1.76. That's our first one. And if I went and found the other one doing the same thing, I'd also find 4.53. That's part A. Part B now says, what's the general solution? Cookie cutter. X equals first positive solution plus the period. We've got cosine going on. period is 2 pi, slap in your n, NEI. That first one, the 1.6, is going to happen every period of 2 pi. Then take your second positive answer, which is 4.53, and add again 2 pi, throw in the n, and define your n as an integer. We're doing multiples of integers. The NEI tells us that we can't just take 1.5 periods. We have to go 1 period, 2 periods, 3 periods, or -4 periods on either way. If there were 3 intersections, if it was 3 places that they had zeros, I would have 3 answers in this general solution. All right, so now I'm going for sine of 3x equals 0. It's already equated to 0, so I'm going to find the zeros between 0 and 2 pi. So let's graph that one, see what happens. Oh yeah, that 3x, that gave us a horizontal stretch by a factor of 1/3. We're going to have 3 periods in this screen that we're looking at. That means we've got answers at 1, 2, 3, 4, 5, 6, 7 answers that we're going to have to find. Oh, that last one, do we get to use? No, we don't get to use that last one because it doesn't equal 2 pi. But we can use the 0 because it does equal the 0. So we're only going to have 6 answers in this one. Using the same process again, finding the zeros. Our answers are going to be x equals 0. The second one is going to be x equals 1.047 ... Well, we want to know where that's going to happen a little bit more exact. Okay, so I've got my second solution there into the calculator. Even though it asked for just the nearest hundredth, I can go to exact form if it is something that's a nice, easy exact form to get to. The way you're going to do this, cancel out of here. Second, quit. Get to your screen. Now, hit X. As soon as you use the intersection or the 0 feature on your calculator, it stores that X value into the X. It actually stores the Y value into the Y, if you want to use that as well. But we only care about the X in this question. Now, if I tried to math frac that, oops, there we go, it's not going to work. Because in an exact solution, the pi is holding me back. So let's pull out the pi. Let's divide out pi. Now let's try to math frac that and put the pi back in. Oh, that's pi over 3. So even though they asked just for the nearest hundredth, which is 2 decimal places, I could say that this is pi over 3 as well in exact form. Let's go through. I'll just give you all the rest of the answers. Next one would have been 2.0943951, then 3.14159. Oh, that looks like pi. X equals 4.1887902. And 5.2359878. There's your 6 answers in this domain. To the hundredth, you get 0, 1.05, 2.09, 3.14, 4.19, and 5.24. General solution. All right. So, looking at this, back to our graph. We had on the way up, on the way up, on the way up. Those 3 were on the way up. On the way down, down, down. Those ones are related. So we've got up, up, up. We've got down, down, down. The yellows are all related, and the blues are all related. In our general solution, we only have to look at one set of those. So the first one is 0 plus, well, the period. First positive plus the period. Well, we've got to now look at the period is no longer 2 pi. Period is 2 pi over the b value. Our b value is 3. So we're going to put 2 pi over 3. Slap in your n. Define your n as the set of the integers. Well, you know what? We don't need to say 0 plus. We'll just say 2n pi over 3 nei. And the second one, the blue ones, is 1.05 plus same period, 2n pi over 3 nei. Yellow ones, blue ones. Hey, changing this to our example 2. What would be the exact roots? Assign a 3x equals 0. I showed you the process to get the exact roots. Go through and do it instead of in decimal form, in exact form now. And now we've got a trig function and a non-trig function. As soon as those happen, the general solution is going to be slightly different. And that's really what they're saying here. When they ask for the set of real numbers, that's the same thing as saying the general solution. Let's graph it and see what we get. All right, so punch those two in, cos of x and x squared. I'm going to find the intersection between the two. We graph it, and we see one intersection between 0 and 2 pi. One intersection there. Is that intersection going to happen over and over again every period? That's the question now. So there's between 0 and 2 pi what it looks like. Blue is cos, the green is x squared. If I extend this, if I extend cosine, and if I go to infinity in either direction, so on the real numbers, the cos is periodic, but x squared is not periodic. It doesn't keep happening over and over again. This is our first solution, first positive solution, but it's not going to happen again one period later. It's not going to happen again one period back. It's only going to happen there. And then we have another solution that's going to happen there. They're never going to intersect again. So over the set of real numbers, the general solution, in this case, is just those 2 points, which, using our calculator, would have given us an x equals negative 0.82 and a positive 0.82, and it will never intersect again, no matter how big we make our graph. All right, that's it. Finish off your 3 idea questions, and we're done.